It's because I haven't been sufficiently motivated to come, but today I am. I learned that this is the French Science Center, something with apologies to Dr. Swenson that I thought was an oxymoron until somebody told me who Mrs. French was. It's my really true pleasure to introduce Dr. Taylor Ricketts. Taylor is the director of the Conservation Science Program at the World Wildlife Fund. He got his PhD at that institution in California that aims to be as good as Duke but doesn't quite get there. Nonetheless, studying with Paul Ehrlich gave him the start that he needed to go on and do really wonderful things about conservation. And he's going to talk today about putting ecosystem services on the map. Taylor.
Okay. Thanks, Stuart. Thanks for inviting me to be part of your seminar series, and thanks for coming to spend an hour or so hearing about my work. So, the thing I want to talk to you about today is putting ecosystem services on the map, and that's got a sort of literal and figurative sense. Figurative in that I think ecosystem services are this great idea, but as a science community, we have largely failed to deliver the information that make it an operational force for conservation. So I want to talk about how to get it on the map in that sense. Also, I think one of the mechanisms to do that is actually to make spatially explicit maps of ecosystem services and their value. So that's the literal sense of this title. So I want to tell you about 3 projects that have sort of gotten me in my research program toward that, I think. The first thing I want to do, though, is just explain where I work, because I get this question a lot when I come visit universities. So I thought I'd just sort of say it once and for all with a couple of pictures. I work in the Conservation Science Program at WWF, and we're about 25 people, about half of whom have PhDs, the other half have masters, many from Duke, frankly. And we have a whole raft of interns and students and postdocs coming through for various phrases. And essentially, our roles within WWF, in terms of what you can do with a science degree, is twofold within WWF. It's to do research projects that inform conservation. So we tackle research questions whose answers can help WWF do conservation better. And we serve as advisors to WWF field programs in terms of the science of what they do. So there's this fun duality of doing research projects and applying what we learn, but also what the research community has learned into sort of practical guidance for field programs. So that's kind of the basics of what our science program does. All right, so back to the topic of the talk itself. Ecosystem services, I think everybody here knows what that phrase means, but it's the range of things that natural systems do or ecosystems do that benefit or support our lives. Everything from crop pollination to medicinal plants to provision of timber and food, watershed protection, and so forth. And the reason that WWF is really interested in this as a topic is that it, of course, links conservation of nature and biodiversity, to big issues in the world, human welfare, livelihoods, and so forth. Often these are issues that have more political traction and more funding and more buy-in, so it's a way of broadening the constituency for conservation, to sort of link the idea that conservation can be good for us as well as for the species that we talk about. So it provides, I think, 2 things, and they're separate and important to separate. One is new motivation, new arguments for conservation, sort of other reasons that get to your pocketbook or your economies for conserving things, but also more tangibly new funding for conservation through payments for ecosystem services. So a new way to be paying either private landowners or others that control resources for conserving, and that there are beneficiaries also that are willing to pay for their conservation. So the promise is enormous, and it's definitely got the rapt attention of NGOs like the one I work in. But I also think they're pretty poorly understood, and many of the people I've spoken to here agree and are working on improving that understanding. And like I said at the very beginning, I think the scientific community has largely failed to deliver the science that decision makers need to make sound choices about ecosystem services. So I just want to pause here at the very beginning and say, I work at a wildlife NGO, like a conservation NGO, so this sort of take on conservation to do it for our sake by no means competes with or replaces these traditional arguments for conservation based on ethical or moral grounds, right? There still is a reason in and of itself, intrinsic reason to conserve biodiversity. This is a way, though, of broadening that argument and constituency. To me, that it sort of goes without saying so much that I literally don't say it. And so this time I'm trying to remember to say it up front. Okay, so this whole idea that ecosystems benefit our lives has been getting growing attention. Sort of a sounding gun really was the Millennium Ecosystem Assessment, although there was work done before that. You can just track the number of papers published over time, and you can see right about the time that the Millennium Assessment was getting going and starting to publish its stuff, this huge upswing in the number of citations about ecosystem services in the published literature. But I think most hopefully is that it's getting out of the research community and into things like the cover of The Economist, trying to get into the popular psyche that ecosystems have value, that value supports our lives, and that could be worth money and turn itself into payments for conservation. So what I want to talk to you about is 3 projects, to sort of tell you 3 research stories that get increasingly broader in scale and ambitious in the number of services over time. So here's sort of an axis to sort of array this, in my mind at least. The number of services on the x-axis and the spatial scale of assessment on the y. And the Millennium Assessment is this mother of all analyses, right? So it's this huge global effort, 5 years, UN funded, 1,000 scientists to assess ecosystems, their rate of decline, and the impact on human well-being. And they came up with big top-line numbers. 60% of ecosystem services are in decline, things like that. Great attention-getting stuff, but no one's making a decision at the scale that matches, and so it's not informing anyone's particular decision. But lots of services, global scale. And what I want to tell you about is sort of 3 other projects that array on this. So the first is a case study of pollination in one place with one service, pollination. Just trying to do the best job I could on doing the ecology and then the economics to estimate the economic value of tropical forests as sources of pollinators, and I'll tell you about that. A second study gets a little more ambitious, just trying to synthesize my study and a bunch of others that are like it to try to get at general patterns of landscape delivery of pollination services. So it's still one service, but it's trying to be a little more broad and a little more general, trying to a little more sort of decision relevant in that sense. And then a third one called the Natural Capital Project, which is trying to tackle multiple services at the same time at broader spatial scales where I think big conservation decisions are made to try to get toward this more policy relevant corner of the graph. Can you guys hear me okay in the back? Tell me if you can't, because my voice has been failing for a couple days. So, all right, so let's do those 3 in order. So the first one is crop pollination. So about 2/3 of crops or crop plants in the world require pollination to set full marketable fruit. They vary in the degree to which they need it, but about 2/3 of crop plants require it. Honeybees have been the sort of workhorse of crop pollination, especially in this continent, but their decline through colony collapse disorder and lots of other things has people asking whether native bees can do the job. If our workhorse introduced bee that we keep in boxes is crashing, can wild bees do the job? And if so, what kind of habitats do we need to conserve in these agricultural landscapes to keep them around and pollinating our crops? So here's some examples of the foods you enjoy, if not daily, then hopefully often, that require pollination to set full fruit. So apples and blueberries and fruits of all kinds. This one's a twofer, chocolate-covered almonds, both cacao and almond, obligate outcrossing plants. Coffee, which I'll talk more about. Even the agave that leads to tequila. So next time you're having a tequila sunrise or a cup of coffee, as I'm sure many of you are now, thank pollinators for that. And chocolate-covered almonds. So I'm going to tell you about a coffee study. So the point of this study was to ask, what's the value of native habitats as sources of pollinators to surrounding crops? So we're asking forests as sources of pollination services to surrounding crops. They wanted to ask about bee activity. So does pollinator activity decline with distance from native habitats? If you're closer to a forest and you're a farmer, do you get more bees visiting you? And the second question is, does it influence yields? Does coffee care about that? So more bee activity, does that actually translate into different coffee yields? And so that's the sort of big question and the two sub-questions within it. Where I went to do this is in Costa Rica, and found a really large coffee farm, which is denoted in this map in yellow, surrounded by a lot of other heterogeneous land use, which I just stippled away. But it's coffee and cane and pasture. And then importantly, some forest patches that abut this coffee farm. And the farm's big enough that I was able to put in these distance gradients away from two different forest patches, so I could replicate the distance gradient at least once, and came up with 3 distance classes of sites in coffee at different distances from forest, at about 100 meters, 0.8 kilometers, and about double that at 1.6 kilometers. So I had this distance gradient in the farm, into coffee, away from the nearest significant forest patch. And we just went to all those blue dots and watched bees on coffee plants. Set number of flowers, set number of minutes. Timed observations to come up with diversity and visitation rate of bees to coffee when it's in flower. By the way, if you've never been where coffee flowers, it flowers across the whole landscape at once in response to a rain. So it'll rain, and 7 days later, at least in my system, to the day, every coffee flower that's ready will burst that day. And so it just looks like popcorn fell from the sky, and you can smell it as you drive around, and the bees are audible. So it's quite an event. And here's what we found in just doing these bee observations. So you'll see a lot of graphs like this with the near class, the medium class, and the far class. And here I'm plotting just number of visits standardized per flowers and time. And it's just showing you that coffee plants near the forest got twice the visitation rate as those in the medium and far distance classes. So a lot more bees arriving if you are a coffee farmer near forest. What's interesting, though, if you look at the Apis mellifera, these are these introduced honeybees, right? They're from the old world. And they are kept as honeybees, but also have gone feral, and they've gone feral in this landscape. Their visitation rate's constant across all of these distance classes. So the difference in the near class is these 11 other species of native bees. That's what's doubling the visitation rate in the class near forest, this native community of bees. So you can pick stigmas from flowers and press them on slides and stain them and count pollen. And we get exactly the same pattern, a doubling of pollen deposition on stigmas in the flowers near forest as far away. So this visitation rate seems to be ramifying at least to pollen deposition rates onto coffee flowers. So then we wanted to ask if coffee cared, right? So will coffee produce more given this pollination service? So we went back to those same 12 blue dots on the map, these distance gradients, and treated replicate coffee plants in 2 different ways, some branches one, some branches the other. We left some branches open for ambient pollination. That just measures how coffee would produce with the ambient pollinator community. And we hand pollinated others to ensure sufficient pollination. And these are sort of standard pollination ecology, pollen limitation experiments. And the logic of these experiments, if you're not familiar with pollination ecology, is to ask whether ambient pollination levels are sufficient. So here are made-up data, but it'll make seeing the real graph easier when it comes. So here's the hand-pollinated treatment and the open treatment and the open circle. And if they're the same, that means we added pollen and the plant didn't produce any more. So it's getting sufficient pollination already from the ambient community. And that's that result. So that's a signal that ambient pollination is sufficient. They're getting the pollination services they need, these bushes. But to the extent that the hand-pollinated treatment is higher than the open one, that's evidence that there's pollen limitation going on. We added pollen and it produced more. So they're limited by their pollinators. And these are sort of around zero because we just took residuals around plant means to standardize all the other plant variation in the system. So here's what we found. Here are these same distance classes. And again, near, medium, far. In the near, medium classes, no difference between the 2 treatments. In the far class, the difference that I alluded to before, showing that there's significant pollen limitation in that far class. So sufficient pollination, insufficient pollination far from forest. So to come back to these questions on this first one, does pollinator activity decline with distance from forest? Yep, both in terms of visitation rate and resulting pollen deposition. And does it influence yields? Also yes, and the magnitude of this difference is hard to discern from this residuals graph, but it's about a 20% decrease beyond 1 kilometer from forest. So coffee farmers that far or farther are producing that much less. So we can back from those particular questions to the overall one and ask, okay, what's the value of these forest patches? And we have the data we need to do that now. So let's just say for simplicity that the forest effect is about 1 kilometer. So if you're beyond 1 kilometer, you're yielding 20% less. Here are the two yields in those two zones, the zone within 1 kilometer and the zone beyond 1. And these two numbers differ by 20% around a farm-wide mean that they reported to us. By the way, this unit is Fanega, which is 200 liters of fresh-picked coffee, which I just thought was cool to keep in there. I sort of stripped out all the other weird units, but I just thought I'd keep that one in. So Fanega, now you know. And then net income, their farm reports to us is $35 per Fanega. So that's what they can sell it for minus what it costs them to grow and pick it. So once we have all these numbers, we can just do a thought experiment where we remove the two main forest patches that I pinned these transects on and ask how much more area is now far from, in the far class, too far from any forest patch, and what's the loss in yield. And the answers are 480 hectares become newly beyond 1 kilometer, and the loss of income to this farm alone is about $62,000 a year. That's gross revenue. So that's an estimate of the marginal value of these two forest patches to this farm for the pollination service that they provide. So just to put these numbers in context just a little bit, Costa Rica, I was talking about this today, has this fantastic progressive law that actually compensates landowners for ecosystem services. And they've had variable trouble keeping it funded, but there is a law in the books to give environmental service payments, and they state which services they'll pay for. And they'll pay roughly, again it varies, but $42 per hectare per year to either keep or restore forest on your land in Costa Rica. So that's a statement of the value they put on a hectare of forest. But if you just divide my total by the hectares involved, you get almost 10 times that for one service to one farm alone. So there are these great new sort of programs to compensate for ecosystem services, but there's evidence from here and lots of other places that they undervalue ecosystem service flows by quite a lot. And even my number is an underestimate because there's other services being supplied, other farms surrounding those same patches, not just the one I studied, and so forth. So it's just a sort of final slide to put these values in context. This $400 per hectare per year, by the way, is also right about in the middle, at least when I did the study, of other returns to agriculture from a hectare of land. So sugarcane was higher, return to cattle was about the same. Other land uses were a little bit low. So it's in the same ballpark of returns to agriculture of various kinds. All right, so that was the first one. The case study, pollination services in one place. And now let's move on to the next one, where we're just going to ask, how general is that coffee result? So it's a great case study, and I think the science community has done a really good job of putting a lot of those case studies in place. Individual services, individual places. But I think one of the things we need to do to become more relevant to policy decisions is distill from that some general lessons about scale of delivery or economic value and so forth. So here's an attempt to do that for crop pollination. So this is an NC's group that was led by Claire Kremen and Neil Williams. We've been working for 3 years now. And one of the papers was to ask this distance effect across all these different studies. So 23 studies, almost all of them now are published from 10 countries, and here are all the different crops. And the question is, are there general lessons across these? Whoops. What we chose to do was model the decay of different pollination services against distance more continuously than I did before. So I had near, medium, far. Now we just have a negative exponential function that fits, in this case, native visitation against distance. And it's just governed by alpha intercept and beta, this decay constant. It's a really common way of modeling decay processes of all kinds, diffusion gradients or dispersal ecology. So it's got a good sort of basis in the literature and a really simple 2-parameter decay. So that's how it fits the data that I've shown you in the first part. And we just fit that kind of function to all 23 studies that we were able to assemble in this NC's working group. And you can see that some decline, some fit really well, some actually go up oddly. But the idea is what's the consensus decay rate? So what's this consensus beta from all this information? So to get at that, we used hierarchical Bayesian modeling, which I won't go into, probably to everyone's relief. But the basics are, what we're trying to get at is a probability distribution of the mean beta, or the decay constant that explains all of these data together from all the evidence of all the different studies. So it's a probability distribution of mean beta. The alphas are allowed to fit separately for each study. If a study has a better fit to its particular function, it has more influence over that overall distribution of beta. And we used WinBugs, which is this stochastic sampling approach, to try to estimate these parameters. So again, we're looking at not just the mean of all these different decays, but a distribution of a single decay function that would fit all of that evidence best. And here's part of what we found. So here's this decay rate beta, right? The thing that governs how quickly that function decays. And here are all the different 23 studies. And you can see that both the means and the certainties around them vary a lot. Some are relatively flat, here's 0. Some show a really steep decline, but some have much more certainty around that estimate than others. This is again about native visitation rates. And here's the result that I showed in cartoon form. Here's this probability distribution of the overall mean beta, the beta that controls them all. And you can see it's significantly negative. Here's 0, and here's a sort of hypothesis test about whether it's less than 0. So the consensus is that across all these studies, all these crops, all these continents, there is this significant decline in visitation rate with distance away from forest. And if you plugged up beta and a standardized alpha into a graph, it looks like this. So here's the shape of consensus decline of visitation rate against distance. And one way to get a handle on this is to ask at what distance visitation rate drops in half. And that distance in this case is about 2/3 of a kilometer. So not a bad fit to the study that I did, but it's again across all crops that we have data for. So we can ask the same thing for richness, right? So here's the posterior distribution of mean beta for richness and the resulting graph. By the way, the gray zone is this 90% credible interval, so it's essentially an error bar zone. So we see that richness also declines significantly across all these studies, or the consensus does, but more shallowly than does visitation rate, right? So the point of mean decline is actually at 1.5 kilometers, not 2/3 of a kilometer. And this makes a bunch of sense, and I saw it in my study too, that species are often present, pollinator species are often present far from forest, but not in significant abundances that would affect visitation rate. So this is actually a nice intuitive result that richness of pollinators would decline less steeply over distance than visitation rate would. Finally, we asked for the subset of studies that actually measured yield effects, which is only 12 of the 23, whether we see the same thing for yield effect, measured usually as fruit or seed set in all these crop plants. And we found that a slightly negative distribution, but not significantly negative below 0. And this is what that graph looks like. So essentially not an effect of distance. And I think there could be several reasons for this, where we find steep declines in visitation rate and richness, but not in the actual effect on crop yield. One is that it could be that pollination is sufficient even at really low abundances of these pollinators. So there's only a few of them out there, but they're doing a sufficient enough job. And a lot of crops, including those included in these studies, are partially self-compatible. So it doesn't need enormous visitation rates of pollinators to set fruit. I guess I've already said the second one, that some of these crops are self-compatible, some entirely so. So you might ask why we asked this. If they don't need pollinators, why are they in the study? But we wanted to use every study that we had data on without sort of pre-loading the result to be ones that were just obligate outcrossers. And lastly, I think a sort of operational one, but one that matters a lot, is the experiments are really difficult to do. So it's easier to go watch pollinators than to pollinate flowers by hand. We had to do like 37,000 coffee flowers or something to get our study done. So there's no surprise that there's only 12 of these and that the results are noisier. So I think some combination of those reasons are why in this meta-analysis, we didn't find strong sort of consensus results that fruit or seed set declined. So how does this help? I think there's an answer for ecology and another one for conservation. I think meta-analyses like these are helpful to search for general patterns in nature, obviously. We're looking for that all the time. It sort of distills all these different case studies into general ideas about the landscape ecology of pollination. From a conservation point of view, I think it's important to get much better, as I said at the very beginning, at mapping ecosystem services. And with these sort of general models about how pollination services might decay away from sources of pollinators, we can get at maps like this that have forest patches in green, and then we can parameterize where this yellow zone is and how wide it is. Where's the buffer around sources of pollinators where these services would be flowing to? I think that can inform a lot of landscape planning, and conservation is very often about landscape planning and placing things optimally and intelligently in a landscape. And we can predict the effects of land use change without having to go do these studies, which are, like I said, quite time intensive. So having these sort of synthesized meta-analyses of what we know from everywhere else allows us to predict effects of land use change and inform land use planning without having to spend 3 years in a postdoc doing the study ourselves. And conservation is often in that position of having to make decisions without information. So the more we can synthesize from what we know into rules of thumb to apply where we don't know things, the better off and more informed we'll be as a conservation enterprise. Okay, can you still hear me in the back? Okay. So that was the second one, pollination meta-analysis. Again, as a sort of offsetting to this monster millennium assessment up in the corner. A lot of us, though, who have been doing these case studies and also were involved in the millennium assessment sort of began to realize that something in the middle is actually where the policy relevance lies. So who's making decisions about conservation that affect resource use? No one's doing that for the globe. And landowners are doing it, but it's not a very consequential decision landowner by landowner. But there's this middle ground where watershed managers or state governments or county governments are making decisions about zoning, land use planning, policy, and so forth. And they need for that information on multiple ecosystem services over that sort of meso landscape scale. And those are sort of where a lot of the conservation decisions are being made and where a lot of biodiversity is being affected by decisions. And meanwhile, the scientific community is like bookending this sweet spot of this graph. So several of us sort of saw that and believed that. And also, people coming out of the the Millennium Assessment, Steve Carpenter led a paper that sort of summarized the research lessons of the Millennium Assessment and the needs going forward. And one of the recommendations is exactly this: landscape level quantification of economic values of entire bundles of services under alternative management regimes. So that's this middle ground we're talking about that neither end really addresses all that well. So we started this thing called the Natural Capital Project to try to get at that meso scale. And that's the third of these 3 projects I want to tell you about. So the Natural Capital Project, I might call it NatCap. I'll try not to, but if I do, that's what I mean. Is this partnership between Stanford University and WWF and the Nature Conservancy to do essentially 4 things. To develop tools that map and value ecosystem services, make it a little bit easier for people at those landscape scales to understand where ecosystem services are and what they're worth across multiple services. And we're wanting to test and apply those tools in critical ecoregions around the world to see if those tools work and actually get some conservation done while we're testing them. Support policies to maintain and pay for services, so not just do the science, but stay involved in the application of our results to changing minds and changing policies. And the grand 4th goal is to sort of use that experience from these places where we've deployed these tools to roll up into bigger messages about the benefits people derive from nature and try to change overall minds about the way ecosystems are viewed, from luxuries to conserve when we can afford it to essential capital assets to our livelihoods. So our route to that sort of big message is to show in multiple places that we can map and value services and that it makes decisions better. So since this is a science talk, I'm probably only going to talk about, well, I will only talk about the first two. And those two are carried by a tool set that we've been developing called INVEST. And these are the questions that INVEST is designed to answer, because they're the questions that I hear all the time in a science program at an NGO from field programs who are advising governments and know what sort of information would most inform those decisions. And these are the sorts of things. So what places provide the most ecosystem services? How would a logging project or any land use change you can imagine affect different ecosystem services and biodiversity? What can we expect those changes to be? What landscape pattern would optimize services now and under likely scenarios? That's a big conservation question. And who should pay whom under a proposed PES or payments program, and how much? So where are the sources? Who are the beneficiaries? Who should pay whom? And these are the sorts of things that I think, again, Millennium Assessment and these case studies don't answer so well, so we're attempting at these middle scales. So the idea is to build very simple models that approximate state-of-the-art models on multiple ecosystem services. So for none of these are we state-of-the-science the best, but the idea is to be able to allow multiple services to be simply assessed at the same time. So among those that we're building simple models for within this tool are biodiversity, pollination, carbon storage and sequestration, timber, and that means non-timber forest product production, so medicinal plants, foods, water quality, water quantity, and timing. These are the ones that are built so far, and then these are planned. I think this one's actually not really planned. If any of you has an idea how we can actually make a quantitative model of those, let me know. So I've said this already, but it's really important for this kind of audience, I think, to emphasize that we're trying to do a really simple job of these. And it'd be fun to talk about because it's sometimes a very uncomfortable position to be in as a scientist. But here is the sort of truth that we're facing. So if you look at models and data from a gradient from simple to complex, this is where data are, and many of the places WWF wants this information, right? Super simple data. And any models we can take off the shelf are usually way up here and demand way too many data for what we have. So a good example on the water side is SWOT models, which is a very popular framework for modeling. I've never seen a WWF field project in a position to parameterize anything close to a SWOT model. So do we not help them, or do we try to develop simple ones? So what we've tried to do here and other things in our science program is tier our models and start with tier 1 models that are simple enough to take advantage of the simple data that are available, hopefully to be simply doable anywhere and come up with at least relative scores of importance, and then work over time towards tier 2 models in places we can invest in data collection and get more detail and make absolute estimates of ecosystem services and their values. So I'm going to tell you about tier 1. And just to continue with this pollination vein, I'll tell you how the pollination model within INVEST works, just to see how we're trying to generalize from all this work that's been building up over time. So here's this landscape. It happens to be in Costa Rica. In green are our forest patches, and here's, let's say, a farm that requires pollination. And so the first... All right. So it's not going to animate all that well, looks like. So I'll just do it for you. So the first thing are these yellow A's, pollinator source abundance. We need information, whether it's surveys of pollinator source abundance, so nesting density of something of the relevant pollinators, or it can even be sort of distilled expert opinion about where pollinators would be found. The model allows them to fly onto crops using that distance decay function that I showed you about visitation rate. There's supposed to be sort of graphs that appeared here. I don't know why they didn't. But another function on the farm that relates pollinator abundance and visitation rate to an increase in yield, and usually that's some saturating function. And then the last step in the model is to distribute that increase of value back onto the landscape where these pollinators came from. So we have sources, we have effect at the recipient level, and we sort of attribute that effect and that value, that marginal value, back so we can make statements about the value of these forests as sources of that relevant pollination service. So this is all stuff that's been laid out in a couple of papers, again through this NCES group, trying to come up with this general model. Here's an example of how the model runs and looks in the Costa Rica landscape. So here's the reminder of that map for you. And here is the source abundance, given independent information from my data on where bees nest and find forage in this landscape. So dark green is predicted to be high source abundance of bees, all the way down through yellow and moderate levels, and then white, bad for bee nesting. So you can see that the forest patches are good, given these data we had, and the coffee itself is not so good as a nesting and foraging ground for bees. Contribution to coffee yield, that's that intermediate step where we allow them to fly out into the fields and affect coffee yields through that simple yield function. So again, darker is increased gain in coffee yields, and lighter is less. And then we can attribute that value back onto the forest patches to say where that pollination-relevant pollinator abundance came from. So this is a map of where pollinators come from that affect coffee. And you can see the difference between a forest patch and this map. Since there's not a lot of coffee near this edge of the forest or anywhere else, a really relevant and quote-unquote valuable forest is the one that's near enough to coffee to allow pollinators to fly out and back. So this is a sort of map of source value of ecosystem services, and it's the goal for all of these modules of INVEST to come up with something like this. So luckily we have some, wow, I don't know why it's doing that. Luckily we have some data to validate these models, because I've done all that field work in Costa Rica. So this is predicted on-farm abundance against observed on-farm abundance. So this is predicted from the model. These are my data that I've been showing you for the last half hour. And it's a reasonable fit between what the model predicts and what field data I have for that. And again, the model was parameterized without my data, with other pollination experts in Costa Rica saying where bees might be and how far they might fly and so forth. So I didn't let them see what I knew. So this is the kind of idea. So very simple model, very simple data inputs. You don't need to know that much because often we don't. And then trying to test it against better data when we can to validate those models. So generalizing back up from pollination now to the overall project of the Natural Capital Project, we've been over the last few years testing these multiple ecosystem service models in 4 different places around the world. Hawaii, Sierra Nevadas, Eastern Arcs, and the Upper Yangtze Basin, to, like I said, test and refine these INVEST tools and try to get some conservation done while we're at it. So support them in their conservation goals. Each place and their field teams have clear ideas why they need maps of ecosystem services and what they think that'll get them. But at the same time, we're testing these tools as we go. I'm just going to tell you about one of those circles, this project in Tanzania, the one that I've been involved in the most. That's kind of a project that's grown into its own thing. It's got its own name even, called Valuing the Arc. And it's a big collaboration between a bunch of UK universities, a bunch of Tanzanian universities, and WWF, all funded by the Lever Dream Trust, mostly in the UK. So here's Tanzania, and the focus is this range of mountains in Tanzania called the Eastern Arcs. And they're these range of forested mountains that rise out of the sort of savanna woodlands and Miombo woodlands that Tanzania is famous for, into moist forests and cloud forests, ancient and packed with endemic species. So over 1,000 species of vertebrates and plants found nowhere else, often only on one of those peaks, and over 1,000 species on the red list. So it's on everybody's hotspots list of conservation priorities globally. They also are sort of generally thought to be sources of most of the water for the coastal cities of Tanzania, also sources of food and medicinal plants, and obviously capturers of carbon. So there's some thinking that there are ecosystem service values there as well that continue to be deforested though. And so the idea is being clear about what these ecosystem services values are and where they are coming from could be additional arguments for their conservation. what else to say? So these green blobs you'll see a lot. These are the different mountain blocks that rise out of the woodlands, like I said. And this orange outline are the watersheds that drain them, and that's the definition of our study area. So you'll see that blob a lot. That's what it means. So here are some of the early results, just to sort of skip right to the answer in maybe kind of a unsatisfying way, but I can tell you how each of these work better if you'd like. So here's an early result of our water yield model. So it just is a function of rainfall, evapotranspiration, topography, and soils. And essentially is a map of where rainfall exceeds local use in evapotranspiration. So it's where water is available for downstream use. And there's actually a payments for watershed services scheme in Tanzania now, started by CARE and WWF, to try to get water users in Dar es Salaam, the capital, to pay upstream landowners for watershed management. And they've gotten two groups to buy into it, a Coca-Cola bottling plant and the municipal water supply company, Dawasco for Dar es Salaam, to pay into this fund. But they don't have a lot of information on where they should spend that money to best effect, right? So maps like this about where water essentially is coming from can help them direct those investments. Carbon storage is another one. Sorry, I didn't really say, but the darker areas in this map are where more water is available for downstream use. So it's where it's higher water yield, higher water runoff. Carbon storage, similarly, the dark areas on the map are where denser carbon is, and it's simply a function of storage per hectare estimates from field studies and other syntheses. A land use cover map that this is tied to, harvest of wood products and decay rate of those products over time. So clearly interesting to a lot of people from a red and forest carbon perspective, carbon mitigation in terms of forest conservation. So this can guide red investments where investments in conservation can get biodiversity priorities done, but also can also protect dense carbon stocks. And a third example is charcoal harvest, probably not a big market or payment scheme coming soon for this, but an essential part of people's livelihoods. So this is one of many sort of quote non-timber forest products that model just as a simple function of stock per hectare, access to people, and protection that either allow or prevents harvest. So this is a map, in essence, of where charcoal is available and accessible and accessed. So again, just sort of an overview skim of some of the types of things that these models are meant to produce, skimming over all the theory and math that go into them, but I can tell you about that if you'd like. So we've packaged up all this stuff into an ArcGIS toolbox, which you can get for free off the web, along with a user's guide, and you can enter into sort of a web community of users for this thing. And it installs into ArcGIS and just adds a toolbox with functionality, as I'm sure many of you are familiar with. All the kind of science behind it is being driven chapter by chapter, service by service in a book that we're preparing that essentially, like I say, lays out the thinking, either the hydrology or the ecology behind these models. So we're trying to have kind of a packaged tool that's pretty user-friendly, but also a pretty good scientific basis for each of them that provides that support and foundation. One thing that I didn't expect but should have is that interacting with this tool was actually a really good way to engage people about ecosystem services. So it actually turns into quite a lot of fun to sort of change a parameter, run the model again, see what happens, change a parameter, run the model again, see what happens. This is the non-timber forest product group in the Tanzania project, finding that this is a great way to make ecosystem services and their benefits sort of a tangible way to think about it, and to really understand what drives these production functions that sit underneath this software. Okay, again, always worth, I think, asking why this helps, or does it? How this helps? I think this whole sort of enterprise, whether you use this INVEST program or other things, trying to create quantitative maps of ecosystem services and their values helps in a variety of ways. It helps locate these, quote, win-win areas for conservation. I need to show you combinations of any of these maps with biodiversity, but it's pretty straightforward to do, right? Where is carbon dense? Where are species dense or rare species found? Are areas where we can target as WWF for somebody like us conservation investments that are likely to either qualify for REDD compensation or at least support livelihoods alongside biodiversity. It can target payments for conservation, so I told you about that payment for watershed services idea, and that's a good example there. It can serve to engage those deciding things, so maps are really great, powerful communications tools, and especially interactive maps in a software program we found to be really good on that score. And sort of broadening out, demonstrating the economic importance of nature is the idea behind all this ecosystem services work, and connecting conservation to people in a much more tangible way to sort of broaden the reasons that that conservation is important. So those are the 3 projects, and I guess I just want to say one thing here at the end, and that is progressing up and to the right on this graph has taken me, has sort of taught me this trade-off between the sort of rich nuance and detail of research science that we all kind of crave, and the kind of immediate turnaround, quick and dirty rule of thumb science that is most policy informative, right? So that's an interesting trade-off for all of us to try to think about. How these like detailed experiments on one hand versus this attempt to do really quick and dirty, simple models that get information into decision makers' hands on the other. And I think that's tension is difficult for each of us to try to sort of walk the line between. But I also think it's like presents where the most interesting questions in conservation science are. The ones that are trying to simultaneously be scientifically rigorous and defensible, but also simple enough and approachable enough to actually inform policy in a variety of settings. So it's an important tension. It's one that I think yields the coolest research questions, frankly. It yields the coolest questions that are that can lead to policy impact, and it's also the area in which I think universities like this one and NGOs like the one I work in can maybe collaborate to be together on that interface and that line. So, and I've been spending a lot of time in my 2 days here talking about that in general, not just about ecosystem services in particular. So, thanks for your attention.